At this case, we are still handling examples, questions involving machines. Question number 3, in a pulley system, the distance moved by the effort is 5 times the distance moved by the load. If an effort of 20 newtons lifts a load of 60 newtons, find the efficiency. So we shall say solution. We are given the effort as 20 newtons. So we shall say effort is given as 20 newtons. In our last statement there, the load is also given as 60 newtons. So we write here, the load is 60 newtons. Okay. Remember, they want efficiency. Were we given the distance moved by the effort and distance moved by the load? Let us interpret this statement. The distance moved by the effort is 5 times the distance moved by the load. So the effort distance is not given. Effort distance is not given, the load distance is not given, but the statement says the effort distance, the distance moved by the what? The distance moved by the effort is equal to 5 times the distance moved by the load. You see? The distance moved by the effort is 5 times. So it is 5 times the distance moved by. So if you want to get the distance moved by the effort, you get 5 multiplied by 5 times. You see here? Here. 5 times the distance moved by the load. So when we put that statement in form of an equation, it becomes distance moved by the effort, which is effort distance, is equal to 5 times distance moved by the load. So if I want to know the effort distance, I multiply 5 by the distance moved by the load. So I will simply say, supposing my load distance is maybe 10 meters. So the effort distance, what will happen to the effort distance? As the statement says, it must be 5 times the distance moved by the load. This time is 10. So this one becomes what? 50 meters. So in this case, the distances are not given, but they want you to interpret, because the examiner says the distance moved by the effort is 5 times. So it is equal to 5 times the distance moved by the load. So he has not given you the distance moved by the load and even the effort. But if you want to know the distance moved by the effort, you get 5 multiplied by the distance moved by the load. So you can assume any distance. Supposing the load is 10 meters. This distance you are not given, but you are just assuming. In case it is 10 meters, what happens to the effort distance? It becomes 5 times 10. If this is 1 meter, this one is 5 times 1. If this is 5 meters, this will be 5 times 5. If it is 100 meters, this will be 5 times 100. Is that okay? And whatever you will assume, as long as you have calculated well, the answers will be what? Correct. Now, we have assumed the load distance to be 10 meters. Is that okay? So the effort distance will be 5 times 10, which will be 50 meters. Now, remember, the examiner wants us to calculate the efficiency. So we can say efficiency equals to work output divided by work input multiply by 100%. We said work output is a work done by the load, which is the same as load times the distance moved by the load. We divide by effort times the distance moved by the effort. That is the work input. And then we multiply by 100%, the way it appears here. Now, if we are to substitute, what shall we get? The load, we are given the load here as what? 60 newtons. The effort is what? 20. So our load is 60. Then here, what is the load distance? We said it is 10, assuming it is 10. So you write here 10. Then the effort we were given was what? 20 newtons. So you write here what? 20. Multiply the distance moved by the effort. We say it is 5 times. You see, it is 5 times the 10 for the load. So it is what? 50 meters. So multiply here by 50. And then the formula says multiply everything by 100%. Now, if you do this calculation, you will get 60 times 10. The numerator will be 600. The denominator of 20 times 50 is 1000. Then you multiply by 100%. Okay? Now the zeros can cancel. Shall cancel the zeros, or we just multiply. This is 0, 1, 2, 3. You see? 1, 2, 3. So our answer will be 60. So our answer here will be 60. Remember, this is efficiency. The unit for efficiency is percent, not percentage, percent. So our efficiency, which has a symbol that, therefore our efficiency will be 60%. That is one way of calculating that, using work output and work input. But we could also use the other way of mechanical advantage and velocity ratio. Let us see how it works. Okay? Now, we could also say our mechanical advantage, you get it as load over effort. The load given there, as you can see, is 60. The effort is 20. So we get 60 newtons as the load divided by 20 newtons. The newtons will cancel. You remain with 60 over 20. And the answer will be 3. That will be the mechanical advantage. The velocity ratio, we say the formula is effort distance divided by the load distance. Okay? So the effort distance is the one we calculated, 5 times 10, which is 50 meters. Then the load distance, we gave it what? 10 meters. 10 meters. Okay? So, we shall have the meters cancelling. These meters will cancel this, remain 50 over 10, and your answer becomes 5. So the velocity ratio is 5, while the mechanical advantage is 3. So what happens? We shall say efficiency equals to mechanical advantage divided by velocity ratio times 100%. If we are to substitute that, our mechanical advantage we calculated here is what? 3. Our velocity ratio we got here is what? 5. So we shall have 3 out of 5 times 100%. And if you did that calculation very well, your answer also comes to 60%. So it doesn't matter which formula you use, the answer remains 60%. Now, in this situation, supposing our marks were 4, what happens? Calculating the mechanical advantage, you must get something, maybe 2 marks. So we shall give for the formula a half, substituting a half, and we could give the answer a full mark. Those are 2 marks. Is that okay? Maybe we have given a few marks here. Let's give here 6 marks. 6, supposing there are 6 marks. Those 2 will be for mechanical advantage. Then velocity ratio would also have, the formula could be a half, substitution a half, the answer 1. Those are also 2 marks. Those are now 4 marks. Then the remaining 2 is for calculating efficiency. Can give here a half a mark, formula, substitution, a half a mark. The answer, the correct answer 60, we also give it a half a mark. Then the unit percent is a half a mark. So you end up with all the 6 marks. You see? And you score everything. Now let's look at the 4th example. Find the mechanical advantage of the crowbar in the diagram below. So this machine is called a crowbar. One side there is an effort, and then one side there is a load. So there is a balancing point here. Now when you apply this effort downwards, the load moves what? Upwards. But now we are given from the balancing point, from the pivot up to where the load is 15 centimeters. And from the pivot up to where the effort is 90 centimeters. And the question is, we find the mechanical advantage. Now, they have not given us load, they have not given us the value of the effort. So what we are going to do in such a question, we are going to say, using the principle of moments. Using the principle of moments, and the principle says that the sum of clockwise moments equals to the sum of anti-clockwise moments. You see? Now, this one is pulling the body down like this. Is that okay? But this load is pressing the body down like this. Although it is supposed to move up, but it is pressing down. So this one is moving like a clock. This is anti-clockwise. So clockwise we have the effort. Yes. The effort times the effort distance, which is what? On the side of the effort is 90. The 90 centimeters. Then on the side, the anti-clockwise is the load. It is the load times the distance on the side of the load is what? 15. You see? So you simply get the effort times the distance, 90. Then the load times what? Now, remember we want a mechanical advantage. And we all know that mechanical advantage, you get load divided by effort. So we are supposed to get this load, we divide by the effort. Now, The opposite of addition is subtraction. If this was addition, when this one crosses this way, it would be subtraction. But this is multiplication. This is also multiplication. The opposite of multiplication is division. So we are going to divide. How are we going to divide? We want this effort to go this way so that it will be load over effort. When you bring this load this way, it will be effort over load. And yet we want mechanical advantage is load over effort. So we want this effort to cross this way. So what we shall do, we shall simply leave the load here. And we shall also leave this 90 here. Then we make the effort cross this side of the load. Because this is a multiplication, when it crosses, it becomes division over effort. Is that okay? Then this 15 also will cross to 90. Because this was a multiplication, it becomes a division. So this will be 90 divided by 15. Is that okay? Now, load divided by effort is the same as mechanical advantage. 90 divided by 15 is equal to 6. So our mechanical advantage is equal to 6. Now, assuming we had here 6 marks. 6 marks. Or let's give 4. 6 may be so many. We would have here, for saying, using the principle of moments, can get a half. The sum of clockwise moments equals to that, you get a half. Substituting properly, you get another half. Then the answer, you get a half. Oh, there are 4 marks. If there are 4 marks, we could give 1, 1. Okay, this is a half. Can maintain that one. This is a half, that's 1. We'll remain with the 3. Then out of 3, I could give here 1. Yes, we give here 1. Then here we could also give 1. 1, 2. Let's just give 1, 1. You see? Using the principle of moments, you get your mark. Sum of clockwise moments equals sum of anti-clockwise moments. Substitution until you get the answer. Now, this kind of questions can also be set where the effort is not given, the load is not given, but I've given you the system, how the machine looks like. So what you do, you use the principle of moments as we have just explained. We shall talk more about this when we are now discussing a new topic called the moments. So let us now look at types of machines. Types of machines. Types of machines. Now we said we have very many examples of machines, types. We had the levers, the pulleys, the inclined plane, the gears, the wheel and axle, the screw, and so on. So let's begin with the first type. And the very first type we are going to look at are levers. So what is a lever? What is a lever? So a lever is that machine which has 3 main parts. The fulcrum, which we call the pivot. You have the effort and the load. But we could say these are the simplest and commonest, or would even say, let's use the word here, most common machines. See, they are the simplest and the most common machines. So most of the machines we use, the common ones, are levers. But this is not the definition. So we shall say They have the fulcrum. They have the fulcrum, which sometimes we call pivot. Apart from that, they also have the effort, and they have the load. So a lever has three parts: the fulcrum, which is the pivot, the effort, and the load. Now we have classes of levers. Let's look at them. Classes of levers. Actually, there are three. The first one, they are called first class levers. See? First class levers. What are first class levers? Now, first class levers are levers where the pivot or the fulcrum is in between the load and the effort. So let us say these are levers with the fulcrum. Sometimes we use the word pivot. Is between the load and effort. Yes. So first class levers, these are levers with the fulcrum or pivot in between the load and effort. So what are the examples? Let us look at them. Examples of first class levers are, let's look at examples. Examples of first class levers are, we have a number of them. There is what we call a crowbar, the one we have just dealt with, the example, the calculation we have just dealt with. A crowbar looks like that. But we also have a claw hammer, the one we use for driving the nails into the wood. We have a pair of scissors, the one we use for cutting our hair. Although these days we have saloons, but still we have our brothers and sisters who are using this for cutting. Okay, but we could also use a pair of scissors the tailors use for cutting clothes. Okay, pair of scissors. We also have what we call a pair of pliers. These ones we use for cutting the metals. Some thieves use this one for cutting the fence. If the fence is having a wire mesh, they just use a pair of pliers to cut, because they've already known that the work of the machine is to simplify work. So if they want to come in to attack and have known the fence has what? A wire mesh, they simply use the pliers, pair of pliers. Now, the list is very long. We also have what we call a seesaw. No, all these are examples. So if somebody asked you that what is a lever, this will be very correct. You say a lever is that machine which has a fulcrum. It has three main parts: the fulcrum, the effort, and the load. There are three classes of levers: first class, second class, and third class. What about if somebody says, define What are first-class levers? You say these are levers with the fulcrum in between the load and effort. And this will be very correct. And then when they tell you to give examples, all these are good examples of first-class levers. We are now on second-class levers. So this one we shall say, these are levers with the load is between the fulcrum and effort. You see? So second class levers are those levers with the load between the fulcrum and the effort. There are a number of examples. Let me just draw a simple diagram here. I want you to look at this. You see? This could be a simple diagram showing a wheelbarrow. When you look at this wheelbarrow properly, you will find that the load will always be here. And this one is the fulcrum. And this is where you are holding. This is the effort. So you put your load here. This is the fulcrum, which is now the turning point. And this is the effort. So you see, the load is between the fulcrum and the effort. So that is a second class lever. So let's have now examples. Examples of second class levers. What are those examples? There are also quite many. We shall just pick a few. We have already mentioned one is a wheelbarrow. A wheelbarrow. We also have another one, the nut cracker. You see, nut cracker. We also have the bottle opener. When you are going to drink your soda, you are going to drink your beer, you use a bottle opener, as the word says, to open. We have another one. We call it the pepper cracker. Or the pepper what? Pepper cutter, rather. So these are good examples of second class levers. There could be others. So if somebody says, what are second class levers? You say these are levers with a load between the fulcrum and the effort. And that would be very correct. See, I've even ticked. When they say give us examples, the examples we have here, they are all correct. We are now on third class levers, which is the third part. So these are levers with the effort in between the fulcrum and the load. See, this time we are having the effort. These are levers with the effort in between the fulcrum and the load. Let's also look at examples. So let's look at examples of third class levers. What are the examples? There are quite many. We have the table knife. The table knife, the one we use at the table for cutting bread and so on. We have what we call a pair of tongs. A pair of tongs. We also have the fishing rod. We have the human hand. Oh, we can call it the human arm. The list is long. We could add here. We have a spade. We have what we call tweezers. And we have a broom. And many others. All these are examples of third class levers. You see, a table knife, that one we know it. A pair of tongs, we always use it for holding things. The fishing rod, sometimes the fishermen use it for catching fish. The human arm, see, the human arm. Now like this arm of mine, you see, the human arm. Where I will put this phone is the Lord. Then here, there is a fulcrum. And then in between, there is an effort. So the effort is between the fulcrum and the Lord. So that is all we can say about third class levers, giving the definition, the meaning, and then the example.